Okay, so good morning, good afternoon, or good evening, or wherever you are. So the plan for today is to talk about Frangipani. This is a paper from 1997, so it's a bit of an older paper. The context of this paper is network file systems. And you should think about systems such as Athena, AFS, the Android file system in Athena, Dropbox, sort of a more modern version of this. But the general goal here is to basically share files between a collection of users. The Frangipani itself is not widely used, or wasn't widely used outside of DEC. And so the focus of the things that you should get out of this paper today are three ideas, and ideas that actually will show up over and over in the next couple of weeks. First of all, cache coherence and protocols for cache coherence. Second, distributed locking. And third, distributed crash recovery. And these are going to be three ideas that are going to be, as I mentioned, show up in the next couple of weeks. And in particular, we're going to read, starting next week, two sort of heavy-duty transaction systems, and they build a lot on some of the techniques, or they use some of the techniques that actually Frangipani also uses. And so Frangipani is sort of a more gentle introduction to these three topics before we get to heavy-duty transaction systems. And the idea is also in Frangipani itself is an interesting design. So from a distributed systems perspective, it is a cool system. And let me make that point by sort of contrasting sort of the traditional designs for a network file system. So traditional, or the most common network file system designs, and so if you think about like AFS on Athena, is basically you have a set of clients, and you're just going to make a very simple picture. You have a set of clients, connected to some network. You're going to represent the network basically as a single wire, sharing, a number of file servers. And then the file servers have their disk. And basically, all the complexity. I'll get to cache coherence in detail in a second. All the complexity in this design is basically here at the file servers. So the file servers implement, the file system operations, open, close, read, write, stat, everything, and they write, things to disk in a crash resilient or resistant way. And the clients are really sort of dumb or simple. They don't really do much. Perhaps they do some caching as they do in AFS, but most of it is they're relaying file system operations from programs that are running, like whatever VI runs on your client one, it does an open close, and most of what the client does is relaying those operations to file servers. And one reason that that design is popular is that because like in terms from a security perspective, it is a nice design because most of the the file servers have to be trusted, but the clients don't have to be trusted. And certainly in a setting like MIT, where like the machines are just in public and who knows who installs what kind of software on it, that is a nice property. Frangipani, on the other hand, has a very different design, a much more decentralized design. And in Frangipani, actually, a lot of the file server, it's really, there is actually no real file server in the sort of literal sense of the word, but the clients basically run the file server code itself. So let's say we have two clients, and most of the file system code itself, like the thing that actually has inode, manages inodes, updates files, creates directories, all the code, instead of living on the file server, actually lives on the clients. And the only thing that really the file server share is a big virtual disk. And if you will, maybe a good image to have in your head, or some conceptual image to have in your head, is that the virtual disk is basically like a big SSD drive. And so the file servers just basically share one SSD, one disk with each other. Now, of course, internally, this virtual disk is implemented using a system called Paddle, and consists actually of many machines. And those machines replicate disk blocks. They run PAXes internally to make sure that all operations get applied in the right order and all that kind of stuff. But from the outside perspective, the interface is really read a block and write a block, and so it just looks like an ordinary disk. And so what is interesting in this design, if you contrast the two designs, actually a lot of the complexity in this design is on the client side. And one reason they like that, or why is that you can grow the file system with the number of workstations. So if you increase the number of clients, you basically get more CPU power because you get more clients, and each of the clients can run its own file system. And so a lot of the really heavy-duty computation can just all be done on the client machines and doesn't involve any file server at all. And it is true that in the left side, the traditional network file system design, it's often the case that the performance bottlenecks arise in the file server when the number of clients actually becomes too large. And often in that case, for example, you split the file system in across different file servers. Okay, so that's sort of the so from our perspective, or at least from a distributed systems design, Frangipani is interesting because it's much more decentralized than sort of the traditional network file system designs. And the reason they sort of wanted to explore this design has a lot to do with the use case that they imagine, or that they were targeting. And so I want to say a little bit about the use case, because there were a lot of questions related to that over email. So what is the use case? The use case is basically a number of researchers or engineers compiling, editing, their programs, or writing documents. And so it's really designed, this paper is from a famous research lab in that time, DEC-SURC. And DEC-SURC had tens of researchers, 50 to 100. And they're really, what they're doing is designing a file system for their use case. And so everybody is trusted, all the machines are trusted, all the software running it is untrusted. And so the security side of things is really not an issue for them. All of these researchers are sort of heavy-duty computer users, and so they want to, but mostly they're working on their own private files. They're writing their own programs, they're writing their own documents, and so they just want to interact with the files with a high-performance file system. Of course, they might share, otherwise sharing would not be interesting. So they both potentially share files and directories. And it shows up sort of in two ways. They may work together, collaborate together on writing a paper, like the paper that we're reading today. And so they want to have access to the shared files, for the directory that holds that particular paper. And so there's sort of user sharing. And then there's a second form of sharing that the same user might log into multiple workstations. More than one workstation. And so again, whatever one of the researchers goes to the public library of DEC-SURC or their library and logs in one of the public workstations within DEC-SURC, and it wants to be able to read and write their files from that that machine too. So that's the use case. And this use case has sort of a number of design implications, or design choices that were motivated by this use case. And so one of the primary ones that was motivated by this use case is caching. So instead of leaving the data, for example, all in Petal, and every read and write operation goes through Petal, they want to arrange it so that most of actually the action happens on the workstations. And so that the researchers, since they're mostly working on their own private files, it seems like it make a lot of sense to sort of capture data locally on the workstation. Then as you read and write files, there's like basically no network traffic really necessary. And you can sort of write at high performance. And one way they avoid sending a lot of traffic to a pedal is they have a write back cache instead of a write through. And so if operations happen, actually they just stay in the cache, and at some point later they're percolated to pedal, as we'll see in a second. And so combined with that, like even though they're doing mostly workloads are going to be sort of private, where there's not sharing going on, of course in the case they do share, they want to have strong consistency, or sometimes called coherence. And so meaning that, like, for example, if one user writes a file, then another user on the other workstation reads the file, it'd be great if that user actually saw the changes that the other workstation, the other user has made. And so they want strong consistency. So those are sort of the two design choices that really drive this design, as well as this, basically performance. So, and maybe it's helpful, to think a little bit about like what other use cases could you have for file systems. And so maybe one good one that we talked a lot about is think about GFS. Would GFS be a substitute for Frangipani, or the other way around? Like, how do they contrast? And one way to think about this is that GFS is really a file system designed for MapReduce applications. And so it's a file system where files are not cached. In fact, the files tend to be so big that they wouldn't even fit in the type of caches that we're talking about. The files are basically sort of read sequentially, from beginning to end, and that's it. And then maybe some other computer will read that file because there's some other MapReduce application running on it. And so if you think back at the GFS, there was really no data caching going on at all. There was a little bit of caching going on to keep track of where the chunk servers were, but there's actually no caching of data going on at all in GFS. And so there's also no cache consistency problem in GFS. And so there's a type of applications that they were targeting that just didn't make sense at all. And similarly, in GFS actually is not really a real file system in the sense that it was not intended to run like VI, GCC, and so didn't provide like strict sort of POSIX or Unix compatibility. In Frangipani, you can just run your standard Unix applications, and things just work out. And the applications behave in the same way as if there was not a distributed file system, but basically a single file system. And again, in GFS, there was not. Was basically a little library, that actually application used to sort of read and write files in GFS, but it was not like 100% Unix compatible at all. So to give you a sense that these workloads drive really the design of these different these systems. In the case of GFS, it's the MapReduce application that drove the design. And in the case of Frangipani, or the shared file system, it's really a collection of users working on some shared file system, but most of the operations they're performing are probably just on files they own, and so it can perform locally. Does that make sense in terms of contrast and settings? So you see, actually, there are quite a different number of file systems around. Like in Zookeeper, because yet another sort of provides this file system interface, but it's not really a file system. It's like more of intended as a coordination service. You wouldn't store big files in Zookeeper. Any questions about this setting?
Can you briefly repeat why having the file server code running on the client machine enhances scalability versus having the client and the file server being on different machines or on different,
Yeah, so for example, if I'd like to go back to this previous slide here, on the left is the network file system, and so if there's many clients, well, let's think there's only one, let me simplify this picture for a second. Let's ignore the second file server. There's one file server, so that everybody can share the files through that file server. Then all these clients will be hammering on that in a single file server. And so all the read and write operations are going to be sent to the file server. The file server does the directory lookup, opens files, does the security checks and all that kind of stuff. So all the computation really for the file system itself is all happening on the file server itself in the sort of traditional network file system design. In the Frangipani, that's not the case. Like in Frangipani, all the file system operations are executed on the workstations. And so if we have multiple workstations, basically, the workload that this file system can scale or can support scales with the number of workstations.
I see. And in the traditional architecture, so every file server contains or stores, let's say, a section of the entire file system, right? So it's not the case that every single file server has a copy of the entire system. It's that it might be partitioned across file servers.
Yeah, it might be across the grid. Like, for example, in AFS, Greg, there are different volumes, and every file servers manage different volumes, and the data of all the users at MIT is spread across the different volumes. But all the data, like from one volume, is going to be in one file server, and so if that file volume gets hit hard, you're going to get performance bottlenecks.
Okay, awesome, thank you.
Any more questions about sort of the setting here before we dive in to more Frangipani? Okay, good. So now the design choices they made immediately leads to a number of challenges. So I want to talk a little bit about the challenges. And the main one that drives almost a ton of the design is, let's say you have one workstation, workstation one. So in those days, people had workstations and laptops were actually not really existed yet. Today probably would be all kinds of laptops, but so there's a workstation and somebody reads a file, read file F, whatever, maybe the grades database or the grades file, and so that. Basically, that means that file actually is cached, inside of the workstation. And so the client, whatever program running, VI, could update and manipulate the file, and then, sometime later the result will be written back, to pedal the disk, if you will. And so the challenges that are basically around this model are threefold. One, somebody else on workstation 2 maybe at some point do a cat of F. Get at the file F, and of course, it should be the case that at least like we normally expect if we have a traditional Unix file system that you will see the last write to that particular F. So even though the write might have happened at a different workstation, when the second workstation reads the file, we would like to see that data show up. And this is what we're going to be broadly. This broadly comes to cache coherence. And other words, synonyms for coherence are cache consistency, which is like the term that we have seen more in previous papers. But in the sort of out of the computer architecture world, actually, the term coherence comes from that world. And so you can think about them as synonyms. Two, the second problem that that's going to occur and that we need to deal with is that, let's say that workstation 1 and workstation 2 both want to create a file in a shared directory. So like here, workstation 1 creates a file F in the directory D, and workstation 2 also creates a file, say G, in directory D. And we want to arrange it at least that, like, if workstation 1 makes the changes and then workstation 2 makes the changes, that like both files appear, and that like one file doesn't overwrite, say, the directory of the other, or basically overwrites the directory in a way that actually the other file sort of disappears. So this has to. So the second topic here really is automaticity. These operations of creating a file really has to be sort of an atomic operation so that they don't get interleaved and then we get wrong results. And then the final problem that we need to deal with is that workstation 1 might crash while doing one of these complex file system operations. And so there has to be a story, how actually the file system recovers. And so this is really a story about crash recovery. So for example, like in this first case where like a workstation makes a file in the directory D, there's actually a complex operation. The directory needs to be modified, an inode needs to be allocated, an inode needs to be initialized, and then the inode number needs to be written into the directory. So there's multiple sort of file system operation involved in it. And we want it to be the case that if the file system crashes between any of these steps in this sort of complex file system operation, it better be the case that the file system recovers correctly. And what we mean with file system recovers correctly, at least that its internal data structures are correct. And so, for example, that the inode is not lost because it doesn't show up in the directory, et cetera, et cetera. Or like even that the whole sort of internal structures are consistent. And so this is the topic of crash recovery. And so Paddle basically, or Frangipani, needs to address all of these three problems. And my plan is just to go walk through them one by one and discuss how Frangipani addresses them. Any questions about the top level challenges? Okay, let's proceed. So the first thing is cache coherence or cache consistency. And so the key aspect in the solution that Frangipani uses is there actually is a lock server somewhere. And the lock server basically has a table, and for every file, and actually it's an inode number, but for every file, who has the lock at this particular point in time? So who's the owner? So we might have a file F, and it basically says, works, and for which the lock server has a record that the workstation 1 owns that particular lock. And the lock server itself is a distributed service, and you can almost think about it as sort of almost like Zookeeper. It provides acquiring and releasing of locks. It's fault tolerant. In the case of Frangipani, they do some Paxos-based implementation, but it's spread over across multiple machines, highly fault tolerant, et cetera, et cetera. So that's the lock server. It turns out that the workstation sort of also keep a table for their locks. So here's workstation 1, and there might be let's say workstation 1 caches file F and G. Maybe H is cached by workstation workstation 1. H is maybe cached by workstation 2. And then workstation 1 has a similar table, and they have a list for where every file or for every lock that it holds, where it's either busy or idle. So like it may be F, the lock status is busy, and that really means that actually the file server is just operating on that file. So it's actively using that file. And there's a second state, namely, let's say we have file G was also cached there, and maybe G is actually in the state that they call idle. That means actually that G at that point is not being modified or not being worked on by the file server at that particular instant in time, but it's basically what they call a sticky lock. So that if the file server at some point soon is going to use G again, it can actually do so without actually having to communicate with Paddle or reload its cache or anything like that at all, because it has a sticky lock. It knows that nobody else actually has acquired, no other workstation has acquired the lock in the meantime. So that's the sticky lock. And it turns out that these are the sort of the two building blocks that then being used to what they call what is called a cache coherence protocol, a set of messages or a set of rules that are being followed to actually get cache consistency. And the basic rule is that the guiding rule is to cache a file, you first must acquire the lock. And we'll see that that sort of rule is sort of the stepping stone for actually getting cache consistency or cache coherence. And I'm going to make a small simplification. In the paper, they described locks basically being exclusive or reader-writer locks. I'm just going to assume for the rest of the lecture that they're exclusive. It doesn't really matter. But there's an optimization that basically multiple workstations can have a file cached in read-only mode. Okay, so with that, let me talk a little bit about sketch out the protocol that Frangipani uses. And again, cache coherence or cache consistency, the goal actually for, even though the file system is distributed, it should behave like a single file system. So if you only have one file server, you want to basically that the same results will be returned by the distributed file system. And so you can't tell the difference whether it's distributed or not. And so this is actually remind me of like linearizability. So in fact, I believe actually what Frangipani shoots for is actually linearizable file system operations. Okay, so we got the lock server. We got workstation 1, and there's workstation 2. And there's sort of 4 messages that are of importance here. There's namely requesting a lock, granting a lock, and revoking a lock, and actually releasing the lock. So those are the 4 messages that fly back and forth between workstations and the lock server and lock server and other workstations. So let's look at this. Let's say the lock server has nobody has any locks at any time. So let's draw some timelines. And workstation 1 wants to read write file F. Basically sends a request for a lock, to the lock server for file F. So the workstation can't do anything really at this point yet. The lock server checks its table, sees that F actually is not used by anybody at all. Lists workstation 1 as the lock owner and sends basically a message back granting the lock for F. So at this point, workstation 1 acquired the lock for F, and now it can actually read and write, or now it can actually read, the file from pedal. And actually can make modifications to it too. And all those modifications just stay local. Nothing really happens. It's a write back cache, not a write through cache. And so it stays happily on the client side. In fact, the workstation can even release the lock, here and basically, go from busy to idle. And so if it actually would need to lock again, for example, wants to write F or read or write F again, you can actually do the completely local without any interaction with the lock server. There's a slight simplification here. There's, as we'll see in a second, that a lock has a lease associated with it, so the client at least has to refresh the lease periodically, but it doesn't have to read or write, reread the file F from actually pedal if the lease hasn't expired. Okay, so the instant case, of course, happens like, what if workstation 2 wants to read the file F, and so what will happen? Let's say workstation 2 wants to read, and basically it will do the same thing. It will send an acquire or a request message to the lock server saying I want F. And the way it then works is that the lock server actually looks at this table, sees that F is actually owned by workstation 1, and then it will send a revoke message to workstation 1 asking the lock back. So it will revoke F. And at this point, pedal actually has to do a little bit of work, Frangipani actually has to do a little bit of work, because we have to make sure that workstation 2 observes the writes that workstation 1 has done. And so the way that is done is that basically at this instant of time, the workstation 1 writes actually F to pedal. And we'll see in a second that actually writing F to pedal is actually a slightly complicated operation. It's more sophisticated than I'm just making it out to be. But just think about it like at this point, workstation 1 is basically flushing its state related to F to pedal. Once that actually is completed, so like once pedal sort of acknowledged that actually it actually has received all the data, it actually sends a message back, releasing F. And once the lock server gets the release of F, it can update its table, and allocate the lock to workstation 2, and sends a grant for F to 2. Oops. And at this point, the workstation 2 acquires the lock, and now it can actually read all the information from the file F from pedal. At that point, it is guaranteed that it will see the latest changes to the file F, because the previous owner must have flushed the state to pedal before it actually released the lock and gave it back to the lock server. And so workstation 2 is guaranteed to actually observe those changes. And so here's where our strong consistency comes in. Basically, strong consistency are tied to the lock management. Any questions about this?
There's a question in the chat.
Yeah, okay, good. Would we need to write, okay, one question in the chat, let me address that first. Would we need to write to pedal when releasing both read and write locks? Why do we need to write to pedal when releasing a read lock? Let's ignore the distinction between read and write exclusive locks and read-write locks and just focus on exclusive locks. The whole read thing is just a small, it's an important optimization, but it doesn't really change the designer system that dramatically. Any other questions?
So this sort of design would be really inefficient if we have like two different workstations that are both modifying the same file.
Yeah,
like, you just get like cache bouncing back and forth.
Yeah, you would be, if you're two workstations or two different engineers at that server, you'd be banging on the same file. The file would go back and forth, and so it is not really suitable. So you can see here the influence of like the workload that they're designing for. Their really assumption is that basically, most engineers are working on their private files, and once in a while they'll share files, but they were probably not banging on the same shared file. And we're not using Git, but like you could imagine, like if they had a shared code repositories, or you check out your own copy of the code repository, make all the modifications, and at some point you write it back.
I'm sorry, just to make sure, you said you can release the lock while you still have the file in the cache, right?
You can, okay, so I would be very careful with what I meant with releasing the lock there is not releasing it to the lock server, but locally, changing the status from busy to idle. And since, the lock is sticky, it still sits at workstation 1, and the lock server still thinks that actually workstation 1 has the lock. Is that answering your question?
Yeah, thank you.
So what happens if the request from 2 comes while it's busy?
Yeah, that's a good question. What do you think that happens?
Does it just reject it?
No, I think it doesn't reject it, but just waits. It waits until workstation 1 is done, modifying the file F or executing its file system operation, and then the Frangipani code will release locally the lock. We'll see that somebody's waiting for it, and so it doesn't change it into busy, but actually starts flushing all the operations to pedal and then releases the lock. So this comes actually nicely to the second point, which is this automicity point, and so maybe that will make it more clear. Let me talk a little bit about atomicity, because it also uses the same locks to actually achieve atomic file system operations. So using locks. So when, for example, you do a create operation, like you execute the create file system operation, or whatever, create F, whatever the usual arguments. That turns, of course, internally, even though the application makes this create file system call, this internally actually has multiple file system modifications. For example, the directory needs to be modified. Actually, let me do it in a slightly different order. We need to allocate an inode, for F. We need to initialize that inode. So write the inode, and then update the directory. Update the directory to add an entry basically for the tuple F and whatever inode number was allocated for F. So it's a typical way in which a Unix file system implements files. And so we need to arrange that these operations happen atomically, because we don't want to sort of intermediate results be visible to other workstations. And the way that happens is using, by acquiring those locks. You acquire the lock for this particular inode, for example, inode 10. So you acquire a lock for F. I'm just going to use F as the lock thing, but it's going to be an inode number. And then at some point it releases the file system at the implementation itself releases the lock. And again, this release is a local release operation. It doesn't really mean immediately releasing it back to the lock server. It just means changing the status from busy to idle. And so, if at any particular point in time, so we just ask, there's a request coming in for, revoke the lock, revoke F, that request is not actually being served until the file system, the local Frangipani file system in workstation 1 calls the local release operation. And then it sees that when it does the local release operation, it sees that there's a revoke waiting. And so at this point, it's going to flush, its cache state, to pedal. And once it actually has flushed its cache state to pedal, it will grant basically the revoke or accept the revoke and send back a release to the lock server so that then the lock can be assigned to workstation 2. Does that make sense?
So just to make sure, so in this create operation here, we have to modify the inode for, so we have to modify the inode for F and the inode for the directory that contains F because we have to update the references. And so that means that, like technically speaking, we're actually holding two locks, and we have to release both of them before we reply back to the revoke request.
Yes, okay. Absolutely. So, so again, there's a whole section about this over in the paper. I didn't really talk about this in two, but basically they sort of have not very coarse-grained locks, but also not very fine-grained garage locks. They basically have a lock, per inode, and the directory is an inode, file is an inode, and in fact, the directory is nothing else than a file with sort of a specific format. And so really to create F, would actually have to allocate first allocate the lock or acquire the lock on the directory D, and then would allocate or acquire the lock on inode for F. And so it hold two locks. And as you probably have noticed, of course, if as soon as you have to acquire multiple locks, there's a potential risk of deadlock. If like one workstation allocates locks in a different order, you could have deadlock. And so Frangipani follows the rules that basically all locks are ordered in a particular way, and you acquire the locks in a fixed order.
I see. Thank you.
In fact, the locks are ordered by lock number, inode number. Does that all make sense? Yeah. So there's a bunch of more complexity there. Okay. So having discussed sort of the atomicity of file system operations, at least during crashes, if there's no crashes, at least it's guaranteed that these operations happen atomically because the locks ensure atomicity. Of course, it could be the case that like we're unlucky, right? And sort of the workstation 1 crashes like right in the middle of these operations. So for example, it has allocated the inode, but actually has not updated the directory yet. And let's say the crash happens here. And if we don't do anything special, like what is the concern that we might have? Okay, let me, the concern that we might have is that, some file system operation actually is only partially applied to pedal. And, that becomes more clear if we actually think about the scenario, what actually happens in this particular state, like when the state of the cache is actually flushed, to pedal. And so this is the topic of crash recovery. It turns out that actually updating the state in pedal also follows actually a pretty careful protocol. And this protocol is typically called write-ahead logging. And this is probably is a term you already have seen. Many have seen it probably in 6033. Pedal uses it too. It's a very common technique, and it will also play a big important role in the subsequent papers that we'll see. And so Pedal is actually a nice sort of reintroduction to this idea of write-ahead logging. And the way to think about Pedal's design of write-ahead logging, use of write-ahead logging is very similar to any other write-ahead logging scheme. And so, the way to think about it is as follows. We have our disk, our virtual disk, and we just think about the disk as like a long array of blocks. And what they've done is, part of the disk is like reserved as a log. In fact, in the case of Pedal, there's a log per server. But for now, let's just assume there's like one single log, and then there's the file system. So there's part of the disk is reserved for the logging, part of the disk is the file system, and the file system contains of inodes, some data blocks, et cetera, et cetera. And the rule is that when you update the state in Pedal, the first thing you do is actually you first log the update. So when, if we go back sort of to the previous picture, at the point that Frangipani on workstation 1 wants to give back the lock, to the lock server, it first has to write its state, to Pedal, and that goes in 2 steps. The first step is log the update, the description of the update, to the log person. So here, for example, we'll get a record that says like, create, basically describes the create operation. So it will have, whatever, allocate inode number, whatever, basically the result that would have happened if you allocated the inode number and the directory change. And we'll be a little bit more specific in a second, but that's sort of the update contains the modifications that need to be made to happen to the file system blocks to actually reflect, the change. So you first, log to the log the update, and then once you have updated the log, then the second operation that the client executes, the workstation executes, is actually installing the update. And the reason, for doing it in sort of 2 steps is that, once, you've logged all your changes, then it's completely safe to update the data blocks because they always will end up in, or update the file system because it always will end up in a consistent state. And the way to see this is basically, let's assume, the client workstation that was actually flushing its state to Pedal, crashes right here. Is that okay?
Yes, because since everything is logged, the what was it called? Like the daemon recovery service?
Yeah, correct. So yeah, the daemon just can go back to, there's going to be a daemon. When there's a crash, there's basically a daemon, sees if there's anything in the log. If there's anything in the log, it just applies it to the file system. And why actually do this in this way? Why not just immediately update the file system?
Because we can crash in the middle of the update and we don't know what we've done and what we didn't.
Yeah, exactly. Right. So in our previous example, allocating an inode is presumably, to making some change somewhere, like to an inode block, and actually adding the directory to, or adding the file F, to a particular directory, presumably updates a directory block or a data block somewhere. And so these are 2 separate writes, right? 2 separate disk blocks, and they're not atomic. So we would crash between one of the 2. Then we might have allocated the inode, but not stuck it in the directory, right? And basically what will happen if we crash and recover is basically we lose the inode, right? Unless, we could scan the whole disk, but that's very expensive. And so instead, what we're doing is we're basically logging the two changes first, or we're logging a record describing both changes first, and then apply the changes.
So how do we ensure that operation 1 is atomic? So the first log to update.
The first log update, yeah, that's interesting. So the paper's actually not 100% crisp on this, but there's a couple ways of doing it. They mentioned that every log record has a checksum. And so they use the checksum to see if there's actually, so before to read a log record, they read the log record, recompute the checksum just to make sure that the whole record is complete.
I see, thank you.
Another way of doing it, which is a couple way of doing it, is you write, a couple blocks, like 1, 2, and then you write a commit record. And the assumption is that writing a single block, a single 5 in the 12 sector is an atomic operation. So it either happens or it doesn't happen. And so either the commit record says writes are done or writes are not done. And so you can just look at the commit record, and if the commit record is not there, then you know that the operation is not completely recorded yet, and you shouldn't execute any of it.
I see. And also to double check, so in the previous slide, if the crash happens before we flush things to pedal, then this is not a problem, right? Because if the workstation crashes, well, the cache goes with the workstation, but there's no inconsistent state for any other workstation.
That's correct. Yeah, just the data will be lost. That's it. But it will, since it's not written to pedals, there won't be any visibility problem. So it's really, the crash here, correct? That one doesn't really matter in some ways. The one that actually matters is the crash during this flush operation.
Thank you.
Okay, so there's one subtlety in Frangipani, which we'll talk about in a second, a little bit more detail, namely that in Frangipani there's a lock per server, and that's sort of unusual. And we'll see in a second, how that actually creates some problems. And so we'll see that there's a small extension to the protocol to actually make this all work out. Okay, let me say a little bit about what is in one of those log records. Because that turns out to be important for the crash recovery, particularly because we have Frangipani has multiple logs per server. So every log has so here's our log, basically, there are records in it. They have a sequence number. Whatever, sequence number 2, 1, 2, and what the end of the log is if the next sequence number is not one higher than yours. So there's another way they mark it up. And basically, in one of these records, is an array of updates that describe the file system operation. And so it contains the block number that needs to be updated. So, for example, in our case, that would be the inode number, the block that contains the inode that would be allocated. A version number is in that record, and we'll see in a second why that is important. And basically, the new bytes for that block number. And so, for example, in the case of creating a file, creating F, there's going to be 2 entries in this array, 2 entries. One describing the update to the inode block, and one describing the update to the directory block, the data block of the directory. And so basically what happens on the replication, just to make this abundantly clear, correct? When a request to revoke a lock comes in, the first thing that happens is force the log to pedal. Once then is done, send the updates or send the blocks, the updated blocks to pedal. And then release the lock. All right, and this ensures that there's a couple things that we need to sort of think about. if there's no crashes in the middle, then this is as always, as previously described. Really, the interesting case is when a crash happens right after forcing the log to P, but before updating pedal. So let's talk a little bit about that.
Sorry, what do you mean by new bytes?
Good. Let me go back. So with that, I mean the changes to the inode block. So for example, the inode block, maybe you update, some part of the inode and you sort of write down what whatever the bytes that have changed, like, bytes 0 to 512 have the following value, or bytes, 10 to 20 have the following new value.
But couldn't those changes be like, because each one of these blocks is at most 512 bytes,
Yeah.
right?
Yeah.
But the modifications that you make could be like a lot larger than 512 bytes.
There's going to be a record for every block. So in fact, so a couple points. First of all, data writes actually are not going through the log. So this is actually an important point. So thank you for asking that question. So when you write a file, and the application recalls like write file F and a whole bunch of data, all that data actually does not go through the log. That just goes straight to pedal, like once you flush the state. The only changes that go through the log are meta update changes. So metadata changes. And what metadata means is really information about files. So inodes, directories, that kind of stuff, that actually goes through the log. And so the description that you see in here is really, the updates to the metadata blocks, of the file system. So inodes and directory data. And the application level data, like the file blocks that actually constitute a file, those blocks are just written straight to pedal and don't go through the log. And so it's interesting to contemplate, what is the implications of that, like that design choice. What's the downside of not writing everything through the log? First,
The updates to the data, they can be lost.
data can get lost, yeah. What other sort of scenarios are possible? So let's say, the file consists of 10 blocks. We start writing the 10 blocks, what states can the file actually end up?
Be inconsistent.
Yeah, well, yeah, inconsistent could have some of the rights, none of the rights, all of them, who knows what, correct? But it's not guaranteed that all 10 of them will be applied together.
Is this important when you have like this need for atomic rights, or yeah, like if you didn't need atomicity, would this could we get rid of the log?
I think hold that question in a second. Let's first talk about the applications, and then we'll come back to that. Okay. So the applications can't really write, their data atomically through the log, because the data is not written through the log so not written to the log and then applied. So that means that, for example, if as an application you want atomicity of your writes to a particular file, then you have to arrange that for that yourself. And this actually turns out to be the case on most Unix file systems anyway. And so, like in that way, Frangipani doesn't really change the game. If you write a file in the Unix file system, you write like a VM image, it's not guaranteed that like the whole image is written consistently in one single shot, to the file system, even when there are crashes. And so the typical way, people solve this problem in applications is that they first write a temporary file, write everything in the temporary file, and then do an atomic rename, to the destination file name. And so Frangipani basically relies exactly on the same setup as sort of normal Unix would do. So like Frangipani doesn't change the game, and this is why the writes of files are actually not logged, through the log. And what is the advantage of not logging? So clearly there's a downside, right? Because you can't do file writes atomically using the log. You have to have your own plan for doing atomicity. But what is the advantage?
Well, performance because metadata is very small compared to the actual user data
Yeah,
and also memory as well.
yeah, exactly. So so like if you write like a gigantic file, correct? Like say the gigabyte file, that really means you have to write 2 gigabytes. Right? First, write the gigabyte to the log, and then you write a gigabyte, to the disk. And so basically, this cuts performance in pretty dramatically. And so, which is why typically the user data that, is not written for the log. It's very important, of course, going back to this earlier question, it's very important that the internal file system structures are kept consistent, right, and are not inconsistent. And so, therefore, the metadata updates all go through the log. And so that basically, like when you create a file, you need to update the inode block and you need to update the directory block. That's guaranteed to happen together.
So would the data blocks updates go between step 2 and 3?
Yeah, I think you just send them out. They probably after 1, they probably send the data blocks in parallel to as part of step 2 and straight to pedal, to the file system area. Okay.
So I had a question. I think I don't remember exactly how big the log was, but I believe it could span like 2 blocks. Is that
The log is
correct?
multiple. Yeah, the log is multiple records. Could be
Okay,
many
yeah.
records. Yeah.
Oh yeah, that's right. Like up to 2 terabytes. So what happens if we send like a log, like part of a log, and then it crashes as you're sending the log? When we get like an issue with like
That's exactly, this is what I'm talking about. Good, thank you. So there's a bunch of crashes that could happen, right? Like so if we crash, let's consider a bunch of cases. Like we write a crash before writing to the log. So what in that case, what's the outcome?
it's lost.
Yeah, lost. So then we're gonna have the scenario like we crash after writing the log. What happens then? It's actually a slightly complicated scenario.
Is this after writing like the log to pedal?
Yeah.
Then the daemon steps in.
Yes, and then the daemon steps in. And it's a little bit of a complicated story, correct? Because so how does this all discovered? Like what actually happens? So presumably what happens is somebody else wants the lock, correct, on this file that that the crashed workstation holds. And here's where the leases come in important, right? So every lock has a lease, and what the lock server will do, it will not grant, the lock server will ask in workstation 1, please give me your lock F back. Workstation 1 doesn't respond because it's crashed. And what the lock server does, it waits until the lease expires on the lock. And why does it wait until the lease is expired?
I think in this case the server the server that crashed like also knows it didn't like renew its lease, so it can clean up by like its own. Yeah, it can clean up its own stuff. So like what is the what's the fundamental problem here that we're actually trying to challenge? What is like the scenario that we've seen over and over in previous lectures that is always a challenge? Split brain.
The partition?
Network partition, exactly. It could be the case that actually workstation 1 did not crash, but the lock server can't talk to the workstation because of a network partition, but the workstation can talk to pedal, and so it might still make changes, correct? But whatever we guaranteed, as you just pointed out, once the lease expires, workstation 1 will definitely not make any changes. It is not allowed to. It follows the protocol. It's not allowed to make any changes anymore. And so this is so why the lock server waits until the lease expires. Then at that point, it knows for sure that nobody holds the lock anymore, or couldn't hold the lock if nobody's writing to pedal anymore. And so at this point, it will ask one of the remaining workstations to basically what they call the daemon, the recovery daemon, to run the recovery daemon. And the recovery daemon basically will apply, will read the log of the workstation one, its log, and basically apply the operations that are in that log. Okay. And the way to think about a daemon, it's just sort of like this is like terminology. It's typically just a service or a server or a server process that basically does sort of house cleaning or house cleaning tasks, and those kind of services that are sort of not really used continuously. They're often called daemons. And so once the daemon is done, then actually the lock, can be the lock server can reassign the lock or grant the lock to somebody, to another workstation.
But just to double check, so if you crash after writing the log, then you're going to have a consistent state when it comes to the metadata, but the user is not guaranteed to have finished writing the user data.
Yep, absolutely. So there's no guarantees about the user data. So the only thing, the guarantees that like really the logging system helps achieving is basically consistency of the internal file system data structures.
Okay, sounds good.
Which is important, correct? Because it would be pretty bad if the internal file system data structures are messed up. Everybody might lose their data. Okay, so then there's another instant case. What can happen? Okay, so writing the log TP. What happens if we crash during writing the log?
Is this what you mentioned before, that like there are checksums and we can check whether it was like complete or not, or is this?
Yeah. So what? Okay. So good point. So what happens in this case, correct, is that a prefix might end up in the log, correct? But each of the prefix might contain multiple log records of multiple operations, correct? Like whatever, sequence number 1, sequence number 2, the multiple records. If we crash during one of these records updates, then the checksums won't check out, and so we'll basically stop. The recovery daemon will stop at that record. So what will be in the log will be a correct prefix of the operations. So for example, the create of file F is in there, maybe the create file G is in there, but the create of file H is not in there. But each individual record that describes one atomic, file system operation, is in there and is complete. And so what will happen is that basically we'll apply a prefix of the operations that the workstation is doing, and we basically lose the end of the prefix or the end of its updates, which undesirable, but totally okay, because in the other case we might have lost all updates. Like in the first case, we were crashed before the log, we would have nothing on disk. Does it all make sense? Okay, then there's one more tricky case that we need to consider, and that has to do with the fact that actually Paddle has a log per server, or log per server. So I want to talk a little bit about that, and this is related to the question posed for the reading. This is about many logs, and so let's say we have 3 workstations, each with their own log. So here's workstation 1, workstation 2, workstation 3. And workstation 1 at some point does a delete of a file F that happened to exist before. Then workstation 2 does a create of D and F. But that create, remember, is written to its own log. Okay? So this delete is written to the log of workstation 1, this create is written to the log of workstation 2. And now let's say workstation 1 crashes. And then workstation 3, basically, the recovery daemon runs. For workstation 1. And the bad possible outcome, correct, is that it would replay the delete, which would overwrite the changes that workstation 2 made to pedal. Right, so that's the context. And the question is, how is this fixed? And I think the way I would like to address this is by actually having you spend a couple minutes in the breakout room, debate this with each other, or any other aspect of pedal if you want to. And so Lily or anybody else, any of the other TAs, you assign people to breakout rooms?
Should I do it or?
Yeah, that'd be great if you could.
Okay, cool. All right. I'll close them in about 5 minutes.
Yeah, 5 minutes would be perfect.
Cool.
Everybody back? Okay, so just quickly re-summarize. So we have 3 workstations. Workstation 1 at some point deleted the file. It's in the log. Workstation 2 at some point later created the file F. It is in its log. And then 1 crashes, and workstation 3 actually runs the recovery daemon on the log of workstation 1. And of course, it would be a disaster if the delete would be replayed. Because a later create has happened on another workstation, but it's in another log. So the daemon doesn't know it. How is this problem solved? Or how is this potentially disaster avoided?
We set version numbers.
Yep.
Yeah.
So you can say a little bit more if you want to.
Sure. So like it's guaranteed because we had the lock that the operations have already completed for server 1.
Yep.
And so the version number for the log is written in pedal, like the last operation, and so the recovery daemon won't do anything previous to the current version number.
Yeah. Okay. So let's say be absolutely right. So we'll just summarize this. So we have 2 logs, correct, that are actually of importance, and we have some file system state that sits in the pedal, right? So these are the logs, and then here's the actual file system. And here was, like this is directory D, directory D was modified, and the file F was deleted, and that has some log number I, say 10. And this is a workstation 2, and here is a D that was deleting the D, FMD, and here's creating FMD. And what log number will be in this entry? Version number, sorry.
11.
11, yep. Right, because they're basically totally ordered, and the locking protocol will ensure that they're totally ordered. And in the file system with the metadata blocks, like so for example with the inode block for F, inode F, what version number is going to be on the disk or in pedal?
$11.
Yeah, in the case that actually the operation was applied to the file system, it would be 11, correct? And so when the daemon what rule does the daemon follow?
Never replays something that's already been applied.
Yeah, now does it decide if it's applied?
Like the
Anything higher.
version number.
Yeah, the version number, correct? So if the version number, it only reapplies an entry if the version number in the log record, log number, the version number is higher than the inode or the metadata version number. Then replay. Okay. So in this case, the recovery daemon will see that the version number in the log record is 10, which is smaller than 11 or equal to 11, doesn't matter. And so it won't replay it. And so this problem cannot appear.
So does the 10 necessarily not, is it okay such that like the 10 is not on the WS workspace 2's log?
Yeah, it's not there. So like in the work, because the workstation 2 wrote actually the inode after workstation 1, and so its version number would be 11. Basically, when you do prepare an update, the version number in the update record is always 1 plus the current version number in the inode. Okay.
This is a small question, but what does the D stand for in the
Oh,
log?
directory.
Two? Oh,
Directory.
Okay.
Okay. Yeah. We're creating a file in the directory D. We're deleting a file from the directory D. And the update must include, some information about the directory. Okay. So
Sorry,
yeah.
I had a quick question. So are the version numbers like always tied to the specific inode that's being edited?
Yes.
Okay.
And presumably the version number for every update, correct? Like there's a version number for the directory, there's a version number for the file. I'm like showing this a little bit wrong here. Like if you go back to the log record, here basically there's an array of updates, and every update in the array, contains the block number, the version number, and the new bytes.
Thanks.
Okay, so just stepping back and closing off this discussion of this paper. So it's probably the first paper that we've read that basically where the system itself is not the one, it's not like in dominant use, and therefore it's really interesting to talk about. But what is interesting about this system is the ideas in it. And so cache coherence protocol, or cache consistency protocol, distributed locking, the lock servers, leases, granting and acquiring and revoking, and distributed recovery. Where one workstation crashes, but like a daemon on another workstation actually does the recovery. And what particularly interesting is what's interesting is sort of the interaction between the three pieces. And they interact. And what we'll see in the next couple papers next week, particularly not the first day, but the papers after that, which we're going to talk about sort of heavy duty, pretty involved transaction systems. We'll see these three topics come up too. And so hopefully this will help you when reading those papers to understand actually what cache coherence is, what cache recovery is, and distributed locks are. And the other probably point that's interesting to make is that Pedal is really good for useful for the particular setting they designed it for. And the performance part of the paper is a little bit hard to understand because it's like for 9099. But if you look at the graphs, you'll see that the file system basically workload can increase with the number of workstations, and that's exactly what they were shooting for. And and they achieved that goal. Anyway, I hope you find this design interesting. It's sort of not your usual design, and so hopefully it was thought-provoking. And with that, I'll stop. Of course, stick around if you want to ask more questions, and otherwise, I'll see you first day.
Can I ask two questions?
Yep.
My first question was just in general, the cache coherence protocol here is to not have one file cached in two places, right?
Mm-hmm. Yeah.
Oh, okay. And my other question was about there was a page with the log, and you had the log records there.
Yep. Let me go back here.
Yeah. And I was wondering, you said that each like record is atomic, but each record has a number of updates too, right?
Yes. And again, I think the paper's slightly vague here exactly what it does. Either it always fits in 512 bytes, and then a single sector for 512 bytes just is atomic, or they use this checksum trick. So you read 212 bytes sectors, you recompute the checksum and compare it with the checksum stored there, and if it's right, then it must be a complete record.
Oh, okay. So if it's shorter, then good. If it's not, then you do the trick. Okay, I see.
Yeah,
okay,
and I'm not sure what they exactly do.
Oh, right. Okay, thank you so much.
You're welcome. Any more questions?
If you go back or forward 3 slides.
Yep. Here.
There's this. maybe back one slide. There's a section where you talked about how if a crash happens during the middle of a write and we get like, yeah, a prefix in the log, that's like okay or something. Do you mind repeating what you meant there?
Yeah, okay, so so let's go back to this last picture I just showed earlier, blah, 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 here. So here we have so the workstation 1 could have executed many, many file system operations, correct? Each one of them described by one of these by an entry in the log. So like the first entry might be creating file F, the second entry in the log might be creating file G, whatever. The third one might deleting file F. And so there's a whole sequence of operations, because remember, the workstation just keeps executing file system operations as long as it holds the logs, and nobody else wants the logs. And so the log could be contain a whole bunch of file system operations. Now, for each file system operation, for each individual one, there's a log record. And the log record, is the atomic file system operation, the description of the changes that need to be made to the actual file system blocks to reflect that file system operation. And so what could happen, correct, is that the revoke message comes in, the workstation 1 starts writing its log, to pedal, but it just doesn't get all the way to the end. It just happens to crash like somewhere in the middle, like anywhere, right? In that case, basically a prefix of the workstation log is on the disk or in pedal. And that means that basically the last couple file system operations are just lost. And only the prefix will be replayed.
I see, and we're just saying that's okay.
Yeah, we're accepting that outcome.
Got it, thank you.
Because we already accepted to that outcome earlier, right? Because it could even be the case that we got the file system crashed like right before or right after we got the revoke message, but it actually didn't write any log entries yet to the to pedal. Any more questions?
I have a completely unrelated question.
Sure, go ahead.
To 824, but I was wondering if you knew anything about 6858 for next semester. I saw Professor Seldovich is going to be teaching 6SO860.
Yeah, I think the current plan is not to offer 858 in the fall, but we're hoping to offer it in the spring.
Okay, awesome. Do you know what 6SO860 is? I couldn't find much information about it.
There's no information yet. So that's a good question. It's intended to be an undergrad security class.
Okay. Okay, nice.
So like
Great.
6858, but undergrad?
Yeah, sort of like maybe an intro to both 6857 and 6858.
Okay. What's the number?
It's an experimental number. It's one of these experimental numbers because the class doesn't exist yet. It will be offered for the goal is to offer it for the first time in the fall.
Okay, and so is it going to be mostly like content from like, is 858 going to keep its original form, or is it?
You're asking me questions I don't know.
Sorry, yeah. That's fair.
And I think the people involved in designing the class are people that are involved in 857 and the people involved in 858.
Yeah.
I'm not actually involved.
Okay.
Yet another reason, but and they're trying to work out what the curriculum exactly is going to be, and that of course is going to have some percolations for 858 and 857.
Okay, sounds good.
But 858 and 857 are not going to go away. That's the
great. All right. Thanks.
You're welcome.
I have a question. I don't know how quick it is, but in the paper at the end of page or like right before section 7, they talk about a case, a failure where with like the lease expiring and the server not really crashing.
Yeah. And
then talk about like basically that there's no real solution to this.
Well, there is a solution. There's a real solution. Okay.
With like human intervention.
Yeah, okay. So I think the problem here really is the sort of the theme of the paper was like, Petal and Frangipani are designed independently, and that has a lot of nice properties. And this is one place where it would be very helpful that Petal has some support, to help Frangipani along, and that support would be actually have a timestamp on the write to Petal, so that Petal can see when a write actually is out of basically too old.
Okay. So unless you do that, you need to like fiddle around with like the margin.
Yes, exactly.
Okay. And what happens if that error occurs like outside of the bounds of the margin?
I mean, that's a cool. Basically, you get an old write, showing up in the. Basically, somebody else might have at that point gotten the lock on the file, correct, and starting writing to it, and then this old write shows up and basically presumably overwrites some part of it.
Okay.
So we'll break
Alright.
consistency.
Sweet. Thank you.
You're welcome. Okay. I guess we'll stop with that.